So yeah, I'm going to talk about spin Leonard pairs and the proof of the Kresch Tamvakis conjecture. Um, and yeah, thanks for inviting me. And this is essentially a joint work with my advisor, John Kaufman. This is partially was part of my PhD work. So this is us. This is John celebrating our paper being accepted. Um, so yeah. Oh yeah, right. And it was published in the proceedings of the AMS. So yeah, so throughout this talk, D will denote a positive integer, and a matrix B is called tridiagonal, or matrix D in D plus one by D plus one by D plus one matrix over R is called tridiagonal whenever its non-zero entries lie on the diagonal, the subdiagonal, or the superdiagonal. And if a matrix is tridiagonal, then we'll say it's irreducible whenever each of its entries are on the subdiagonal, or sorry, when each of its entries on the subdiagonal are non-zero, and each of its entries on the superdiagonal are non-zero. And then throughout, V will denote a vector space over R. So a little more notation. We're going to define the rising factorial of A. So A is a non-negative, or A is a real number, and N is a non-negative integer. A written this way will be A plus 1, A times A plus 2, to A plus N minus 1. So there'll be N factors. And let Z denote an indeterminate. And given real numbers A1 through A4, B1 through B3, we're going to define more or less define the 4F3 hypergeometric series as this series here. So we have the rising factorials of A1, A2, A3, A4 on the top, and the BI on the bottom, and then Z to the N over N factorial. And it's often written this way: the AI parameters on the top, the BI parameters on the bottom here. And then the Z, everything we see, the Z is going to be 1. Just keep an eye out for that. So Z, this will just be a 1. Okay, so now we can get into it. So the conjecture statement. So in 2001, Andrew Kresch here and Harry Tamvakis formulated their conjecture motivated by research in algebraic geometry. They were studying what are called an arithmetic analog of Grothendieck's standard conjectures on the Grassmannian's G2n. And for their work, they needed a certain bound on the Rockoff polynomial. So something called the arithmetic Hodge index conjecture. To prove that, they needed a bound on the certain Rockoff polynomials. But what they noticed, and they were able to prove their result with a sort of weakish, well, a decent bound, but they noticed a stronger bound appeared to hold, and so that from numerical evidence, etc. And so they conjectured that it always held, and here is the conjecture. So for any positive integer D and any integers I and J between 0 and D, the absolute value of the following hypergeometric series is at most 1. So it's 4F3, and then the upper parameters are I plus 1, minus J, J plus 1, and the lower parameters are 1, D plus 2, and minus D, and then 1 here. And so you're going to see this expression a lot. So I guess, I don't know, you don't have to remember exactly, but if you see a 4F3, it's going to be more or less this one, except for maybe at the very end. Yeah, and so just for reference, in that expression with the infinite series, because of how the parameters work out, these are always going to terminate. So they're actually turn out to be a finite sum. But, okay, so on to Leonard pairs. So by a Leonard pair on V, we mean an ordered pair of linear transformations from V to V, from V to V, A star from V to V, that satisfy these two properties. So there exists a basis for V with respect to which the matrix representing A is irreducible tridiagonal, and the matrix representing A star is diagonal. And then there also exists a basis for V with respect to which the matrix representing A star is irreducible tridiagonal, and the matrix representing A is diagonal. And so in this case, the Leonard pair A star is said to be over R. And just to clarify, A star is we don't mean the conjugate transpose, so that that's a common notation, but in this case we just mean A and A star are subject to these two properties, so nothing to do with the conjugate transpose. Okay, and then let me just briefly. The truth is I'm gonna hand wave at the spin Leonard pair stuff mostly, but just to define what a spin Leonard pair is. So a spin Leonard pair is a Leonard pair where there exists two linear transformations, W and W star, that satisfy these properties. So W commutes with A, and W star commutes with A star, and W A star W inverse equals W star inverse A W star. So that is very sort of interesting property, it turns out. And it has all sorts of interesting connections to spin models and other not theoretic ideas. But anyway, for now, we're going to we're not going to go into too much detail there. Okay. So now we're going to try to define a Leonard pair. So what we're going to do is we're going to put values into a tridiagonal matrix here, and a diagonal matrix here. And the values on the subdiagonal are going to be these values, these CIs. It's like these rational functions here. And then on the diagonal, you're going to get this quadratic values here. And on the super diagonal, we're going to get these ones here. So again, another rational function. And then the diagonal of the A star are going to be 3 minus 2AI, where AI is this. And because of the quadratic, and well, the whatever vertex is at 1/2 or whatever, this is actually going to be, these are all going to be mutually distinct values. I ignore that thing I said, but basically you can check pretty easily that these are all distinct. Okay. Yes, so we're going to try to show that this is a Leonard pair. But let's just look at sort of how these look. If you sort of compute one, so for d equal to 3, there's like a 3 here and a 1 here, and then you have they'll always kind of look like that. The first one will have a 3 in the 0, 1 entry, and this will have a 1, 0 entry here. But then you'll get these sort of interesting rational numbers here. And then, yeah, you get these sort of decreasing sequence on the A star. We'll look a little more at some of these sort of things, but we can move on for now. And then what we also need is something called a P matrix, and it has the following entries. So the ij entry of P is 2j plus 1 times the 4f3 hypergeometric series from the Kresch conjecture, or Kresch Tamvakis conjecture. So let's just look at what that looks like if we compute some of these. So if you just plug in j equal to 0, then this just comes out to be 1 here. And so you just get the all ones vector in the first column. And then you get the odd numbers up here. And you get these kind of interesting rational numbers inside here. We'll look at some more of these soon. Okay. So now, what do we know about P? So it turns out that P squared is equal to d plus 1 squared times identity. In other words, in particular, it's invertible. And PA is equal to A star P, and PA star is equal to AP. And it turns out that these three properties immediately apply that it is a Leonard pair. And indeed, it's actually a self-dual Leonard pair. There's no space. There should be a space here. And if you're familiar with this actually follows from the sort of Leonard's theorem and the classification of Leonard pairs. But this Leonard pair is said to have Rock-Off. And it's also known to be a spin-Leonard pair. I guess maybe it was known this before, but by the work of Curtin. Yeah, so that's why spin-Leonard pairs come up, I guess, a little bit. We'll see maybe a glimpse of that later. Okay, so we have a Leonard pair. And let's talk about some polynomials. So we're going to define a set of polynomials, ui or u0 through ud, with indeterminate lambda, and they're going to be defined in the following way. So the u0 is just 1, and then u1 is lambda over 3, and then after that they're defined by this 3-term recurrence here. So there's a bi, ai, and a ci, which are those same entries in that tridiagonal matrix A. And so we're going to say, oh, ui plus 1 times bi, ai times ui plus ci times ui minus 1. And that's going to give us lambda times ui. But what this allows is we can take the previous two values and solve for the next value. So this defines all of them essentially. And turns out that the ui are a special case of Rockoff polynomials. And it turns out you can also show they are equal to this expression here. So if you plug in theta j, the diagonal entries of the A star, you will get that it's equal to 4f3 times the Rockoff polynomial. I mean, it's not times. 4f3 of this hypergeometric series in the Kresch conjecture. So that's kind of the connection between this tridiagonal sequence and this Kresch conjecture. Okay, so this is kind of what they look like. This is the UI. There's a heat map, so the values are given over here by the color, and you can see that when either of the indices I or j is 0, you just get that they're 1, and then you get this really kind of cool wavy pattern here, and you have this sort of interesting semicircle here where they sort of collapse to not 0. These are actually not 0. They're just very small. In fact, if there was a 0, it's isolated. So it's kind of an interesting thing. Okay, we're going to look at one more drawing like this. This is a 3D version. So this is essentially the same picture, but each value is now a rectangular prism, and the height is the value. So this plane here is 0, and then if they go below, it's negative. If you go above, it's positive. And we can see this sort of beginning things all start at 1. And yeah, there's sort of this interesting seawall here where they kind of collapse down after that. And what I'll say is that the conjecture was essentially stating that for any d, if you compute this box, none of these rectangular prisms are ever going to jump out of the box. So that's another way to say the conjecture. And a note of Tamvakis was that an image similar to this one was sent to him by Herbert Wilf, and he said that Tamvakis at least said that it was probably some of the most visceral evidence for the conjecture. But yeah, it's just kind of an interesting picture. Okay, now we need another polynomial, which are essentially just a renormalization of the UI. And to do that, we define certain coefficient, ki, and it's just the like sort of consecutive products of these ratios here, of these b0 over c, bi over ci, and the bi are the ones again in the entries of the AI matrix. And if you compute these, you find that they're just the odd numbers, 2i plus 1. So you can check that. And then we also might use this new variable, which is the sum of the ki, so the sum of the odd numbers. And you might recall that that's d plus 1 squared. Now, what we're going to do is to define vi, all it is vi lambda is equal to ki ui lambda. And by construction, vi theta j is equal to ki ui theta j. And again, ui theta j, as a reminder, is equal to that 4f3 hypergeometric series from Reddit. Okay, now it turns out that the vi satisfies slightly different recurrence, but again, it equates to just sort of a renormalization. But they satisfy similar recurrence, so I'm just going to say it here. So the v0 is 1 still, but now v1 is lambda. Last time the u1 was lambda over 3. There's a slight difference. And then the other difference is the recurrence looks almost the same, but it's actually in the previous recurrence, this was bi and this was ci, but now it's ci plus 1, bi minus 1. And this is still the same, actually, ai. So slightly different. Okay. Now, the ij, so just to go back, that P matrix from earlier, the ij entry from essentially the definition of the P and the result about the ui being the 4f3 polynomial, the pij, the ij entry of P is equal to vj theta I. And so we'll just emphasize two special cases that we kind of saw in that very simple example. The first column is the all ones vector, and the first row are the odd numbers. So that's just something that will come up again. Okay, and now we're gonna use those polynomials to find a sequence of matrices called the BI. So BI is equal to VI of A. So we plug in A into the polynomial VI, and we define that to be the matrix BI. So for example, V1 was just the identity, or just like lambda. And so V1 will be A. And then we do the same thing to define BI star. So that's BI of A star. And since A star was diagonal, and we're plugging it into polynomial, we actually get the BI is also a diagonal matrix with like the JJ entry being VI theta J. So that'll sort of come up. Okay. So here's what they look like. So, I mean, here's an example. When d equals 3, you get matrices like this. So the identity I don't show here, but then you get B1 is just A. But then B2 is a sort of 5 diagonal matrix with a 5 here and 1 here. And then B3 is a 7 diagonal matrix, a 7 here, 1 here. And they'll continue with that. And you get these kind of interesting rational numbers. And interestingly, there's a 0 here. That's not necessarily always the case. For example, here's d equal to 4. And there's no zeros in these special regions. It's not always going to happen. But yeah, so it's 3 diagonal, tridiagonal, 5 diagonal, 7 diagonal, 9 diagonal. And it appears that all the entries are non-negative. That seems to be the case. So let's look at a bigger example. So this plane here is 0. And then what you're going to see are all values going above the plane. And this is d equal to 51. And so this is what they look like. So each slide is like, the first one is the identity matrix, and then I increases. So you're looking at the BI at each step, from I equal to 0 to d equal to 51. And you kind of, yeah, they have this kind of cool, interesting wave pattern. What I will say about this image is it's kind of hard to see the detail at the beginning because the values are sort of small. So I'm going to show another image with the matrices scaled by their largest value. So now this is the identity matrix. And then you get the A1 matrix, the tridiagonal matrix. And then after that, it sort of spreads out. And it kind of has this cool, interesting wavy pattern. And again, it appears that all the entries are non-negative. These are all coming up above the 0. This is the 0 plane. There's nothing graphed below 0 here. So yes, that's interesting. Okay. Let's move on. So what I'll say is we're gonna, in a second, prove that indeed for any D, the entries in these matrices are indeed non-negative. Um, but yeah. Okay. So because PA equals A star P and PA star equals AP and linear algebra, you can show that the same is true for the BI. So PBI is equal to BI star P and PBI star equals BIP. And just for reference, what does that say about this? Like if we take a look at this equation here, BI star is a diagonal matrix. So what this says is the jth column of P is an eigenvector of BI with eigenvalue, the jth entry of BI star, which, as I mentioned a second ago, is VI theta J. So yeah, so that's going to come up. Essentially, all the eigenvectors of BI, columns of P, and all the eigenvalues are the VI theta J. Okay, and then yeah, again, the all ones vector is also an eigenvector of BI with eigenvalue KI. Okay, now the entries of BI are sort of important enough that they have their own name, the PHIJ, or sometimes they're called the intersection parameters. But sometimes they're a little, Leonard pairs are a little more abstract than general, like say association schemes or whatever. And so they might be it might be a little weird to call them that, but people do call them that. Okay, so how we're going to define them is that the PHIJ is defined as the HJ entry of BI. So you can write that this way. So PHIJ, we take BI and we look at the HJ entry, that's PHIJ. And then a couple comments about the PHIJ. They form the structure constants of the BI. So if you multiply BI times BJ, you can find how to express them as a linear combination of the other BHs with the PHIJ, and similarly with the BI star and the BJ star. And then you can swap I and J, and they're the same. And you can cycle H, I, and J, and then that won't really change anything except for you have to change the coefficient, the KI coefficient in the front, or KH or KJ. Yeah. Okay. So one more important equation about the PHIJ is you can express them as a sum of a triple product of the UI. So it looks like this. So the KI, KJ over nu, that's the same as just writing this, 2i plus 1, 2j plus 1 over d plus 1 squared. And what this says is, it's actually, if you look at the equation P, A, I, or sorry, P, BI star equals BIP, and you multiply by the inverse of P, essentially you diagonalize BI, and you then, or diagonalize, yeah, and you look for the HJ entry of BI, and you try to compute it, which is PHIJ, this formula will just fall right out. So that's where this comes from. Okay, that's one way to find where it comes from. Okay, so on to the non-negativity of the PHIJ. Okay, so for this, we need something called the Rocca coefficients. And these are rather complicated for family of functions. And so they are a set of coefficients. There are these W's here, and they take 6 parameters. And these 6 parameters are half natural numbers, half integers that are positive half integers. A, B, C, D, E, and F. And what they give you are real numbers. And they are actually defined by these 2 properties. So they satisfy what's called this orthogonality property here. And this other identity called the Biedenharn-Elliott identity. And technically you need one more thing, which is some base cases, the spin 1/2 Rockoff coefficients. So something you can define in various ways. But if you have those two properties, then and then the base case, these coefficients are actually defined. Okay, so this Biedenharn-Elliott identity is rather complicated and subtle, but we're going to use it in a second. And these Rockoff coefficients might look complicated, but we're going to look at a special case essentially. So in our paper, we were able to show that if you take A, B, C, and D all equal to D over 2, and E and F, E being AI, F being J, you get that this Rockoff coefficient here is equal to a sign change over D plus 1 times the 4F3 hypergeometric series from the Kresch conjecture. So another way to write that is ui theta j here. So sine times ui theta j over d plus 1. So now, if you plug that into this mess here, this Biedenharn-Elliott identity, what you will get is this expression. So you get the signs cancel out, and you get a 2t plus 1 times ut theta h, ut theta I, ut theta j. So this, if you might recall from earlier, might look familiar. It is exactly the formula for the phij with the missing ki kj over d plus 1 squared. And so this is phij divided by those things. So we multiply by them on the right-hand side. And what we would get is ki, kj, d plus 1 squared cancels with this to get d plus 1 here. So you get that phij is a trivial positive factor times the square of a real number. And so it is non-negative. So the phij's are indeed non-negative. And so this is kind of the main sticking point of sort of the Kresch Tamvakis conjecture for a long time. And so from this, we can now prove the main theorem, the Kresch Tamvakis conjecture. So again, Kresch Tamvakis conjecture can be stated this way: for any positive integer d and any integers I and j, being 0 and d, the absolute value of ui theta j is less than or equal to 1. So again, ui theta j, that's just another way to state the 4f3 polynomial. And so the proof goes something like this. So as we saw, the all ones vector is an eigenvector of vi with eigenvalue ki specifically. And we just showed that the phij are non-negative. In other words, the entries of vi are all non-negative. And vi theta j is an eigenvalue of vi. So by the Perron-Frobenius theorem, the absolute value of vi theta j has to be less than or equal to the corresponding eigenvalue for the all ones vector, which is ki. And then vi theta j, that's just defined as ki times ui theta j. And so divide by ki, and you get this expression here. So that's the Kresch Tamvakis conjecture. And I guess now a theorem. And so what I'll say is, this is kind of usually the end of my talk, but since we have more time, I added some stuff. So what I'll say is, for general Leonard pairs, we're sort of unaware when the UI bound implies the non-negativity of the intersection parameters, the phij. So in this case, both are true. The phij are non-negative, and the ui are between 1 and -1. But for other Leonard pairs, maybe you have one and not the other. We don't know. I mean, if you have non-negativity, it implies the bound on the UI. But it might not go the other way. You might be able to have the UI be bounded and not have negative intersection parameters. But for spin Leonard pairs, there is a related pair of matrices whose non-negativity is a necessary and sufficient condition for the UI bound. So I'm not going to go into the details exactly with that, with the equivalence, but I will say that this idea turns out to give us another proof of the Kresch Tamvakis conjecture, assuming we have the non-negative. So we proved the non-negativity of Bhij, and this gives another way to prove the non-negativity of the Kresch Tamvakis conjecture that doesn't use the Perron-Frobenius theorem. So that's kind of why we might care about this, I guess. So I'm going to sketch that here. So it's very specific to spin-Leonard pairs, is what I'll say. But so in my dissertation, I proved the following using the theory of spin-Leonard pairs. And you can just use the Curtin or Nomura and Terwilliger's theory of spin-Leonard pairs to prove this pretty quickly. I mean, or their work, their papers make this pretty easy to do. What it says is the alternating sum of the BI is equal to this matrix here. So P is that same P matrix from earlier, but now we pre and post multiply by, or left and right multiply by this N matrix, which is a diagonal matrix of 1, -1, 1, -1 on the diagonal. And what that ends up looking like is it's kind of like applying a checkerboard sort of mask to P, right? You take a checkerboard of 1s and -1s. The black squares are 1 and the red squares are -1, something like that, or white, whatever. And then you do a Hadamard multiplication with P. That's what this will look like. So we'll look at an example. So here's the sum of the even matrices for D equal to 3. And here's the sum of the odd matrices. And if you take this minus this, so in other words, the alternating sum, you'll get this matrix, which looks exactly like P, but just with the sign changed on these entries, on these sort of this checkerboard of entries here. And I will say that this matrix happens to have all those entries be positive, but if there was a negative there, then it would get changed to a possibility. Okay, and then one more picture for D equal to 51. This is the sum of the odd index matrices, the BIs, though I'm technically cheating a little bit so that it fits into the picture nicely, or looks nice. I'm dividing the column by KJ, so that it kind of looks like the UIs. I mean, yeah, it does. I'm just scaling. And so this is the sum of the odd index. And then similarly, the sum of the even index. And so if you take the difference of those two, you get this picture, which is kind of neat and might look familiar because this is NPN and this is P. So they look quite a bit different. But it's kind of interesting that they sort of have this similarity, right? You take this alternating sum of the BIs and you get something that looks like this with the sign change. And there's some noticeable differences. Every other entry is -1 down here, but over here it's just 1. So again, this is P, this is NPN. Okay. Now, all that to say, well, yeah, now let's get back into that. So we sort of have what this alternating sum is. The alternating sum of the BI is this NPN. Now, what's the normal sum? The normal sum of the BI has a special name. It's a scalar multiple of E naught, or the 0th idempotent of the Leonard pair, if you're familiar. But it's scaled by D plus 1 squared. Turns out, don't worry about that too much. You can show pretty easily that the sum of the BI is in fact sort of this specific rank 1 matrix here, this outer product. And it'll look like this. So the first column will be 1, then 3, then 5, so on until 2D plus 1. And so we have the sum of the sum of the BI and the alternating sum of the BI. So we can take the sum of these two things and the difference of these two things. So adding and subtracting these two things, we get this expression, which is an expression for the sum of the odd BI, odd index BI, and then take the difference, and we get the sum of the even index BI, add them and divide by 2. But what we know is that the BI are non-negative. And so these are both non-negative matrices. So that means these are non-negative matrices. And so the JI entry of this matrix here is non-negative, and it's this formula here. And the JI entry of this matrix is this value here, 2i plus 1 plus minus 1i plus j, whatever. And so what this says is, regardless of the sign of the UI, it's trapped between minus 1 and 1. So this is sort of an alternate proof of that the non-negativity implies the Kresch Tamvakis conjecture. And so what I'll say about this also is that this does turn out to be true for all spin-Leonard pairs, but not, I mean, we don't know the non-negativity in this case as of yet. But it does give you that these are sort of equivalent. Okay. And so this is the algebraic graph theory seminar. And so we can I'll talk a little bit about sort of where this came from, or like why we were, well, I'll just say this is a connection sort of to graphs, I guess, an algebraic connection. This kind of got me interested in this, and it was just sort of a surprise. I mean, I found this is in my dissertation, but it's sort of a weird thing. Maybe uninteresting to anyone else besides me, but so if you take let's look at an example. So you take d equal to 3, and so B0 is identity, and then B1 is this matrix, B2, B3. Now we're going to look at the subalgebra of this generated by A naught equal to just the identity again, but A1 tilde is going to be just B2, but A2 is now going to be the sum of B1 and B3. So let's look at what that looks like. So again, A0 is just identity, so I didn't write it. A1 is the same as before, but A2 tilde now is a little bit different. It has 2 entries in the first row and the first column. Okay, now if you do this and you look at, you multiply these together in all possible ways, and you look at the PHIJs, right, the structure constants of this matrix algebra generated by these, they have a certain form. So you put these PHIJs in a matrix, BI. So the HJ entry of BI tilde is PHIJ tilde. Then they look like this. So the BI naught tilde is just identity. Then B1 tilde is this matrix, and B2 tilde is this matrix. And these might look familiar to you. Maybe they are the intersection matrices of a strongly regular graph called the Klebsch graph. So I guess I won't talk about the definition of an SRG too much, but here's a picture of the Klebsch graph. So there's different ways to define the Klebsch graph, but in this case, it's in this drawing, the way that they're labeled is they are the even side subsets of 1 through 5, and they're adjacent. 2 vertices are adjacent if their symmetric difference, excuse me, is cardinality 4. And so in that case, the blue vertices are just the standard definition of the Peterson graph. So the subsets of sites 2. Yeah, I guess I won't talk about you can read this, I guess, if you are interested in the definition of SRGs, but I figure probably most people are familiar with it. But for the sake of time, I'll move on. But the point is, this connection is just algebraic. So it's not, we haven't found sort of a combinatorial structure in here. we found that it's algebraically isomorphic to the distance matrices of this. But it's still rather interesting. I mean, it turns out that for these parameters, this graph is unique. That's not true in general. Or, I mean, well, yeah. Okay. So now, let me just say that this is true, though, for all odd diameter D. What do I mean by true? For all odd diameter D, you can do this same construction. So you take you take the identity, and then you take the sum of the even indices and the sum of the odd indices, matrices. You look at the algebra generated by that, and you look at the PHIJs. They will form the structure constants will form the feasible parameters for a strongly regular graph, specifically these ones, and its complement. So you can just generate the complement by swapping A2 tilde and A1 tilde. And these later graphs are called the maximal energy graphs. So the Coulomb and Moulton and Amer's sort of have this bound. I think they're the ones who first came up with it, but there's the energy is the sum of the positive eigenvalues or not sum of the absolute values of the eigenvalues of the graph. And if you say what's the maximum that it can be, you can come up with a certain bound, and you can then say what graphs achieve this bound. And it turns out it's exactly these graphs when they exist. And Amer's has conjectured that these graphs always exist for any n. And they do exist for n like a perfect square and power of 2 and some other examples. But there are examples that are unknown. But weirdly enough, you get this kind of algebraic connection to this Leonard pair that we talked about. Yeah, this is the formal statement. Looks really messy, but basically it's just saying you take the even sum of the BI, the odd sum of the BI and identity. You look at the structure constants, the PHIJs of these, and then you form them in a matrix, PHIJ. Then they will form the feasible intersection matrices of feasible strongly regular graphs. So again, we don't know that these graphs always exist, but it's conjectured that they exist. And so I think no one's found a reason why they don't yet for these graphs. And the B1, yeah, tilde are okay, irreducible tridiagonal, that part's but anyway, so that's just kind of an interesting thing, and that's kind of how mostly I was interested in the Kresch Tamvakis conjecture. I mean, just sort of as a structure, looking at it, what's interesting about it, and there were some ideas that Terwilliger suggested to us that got me kind of interested in looking at algebras generated by these matrices, and we found this weird thing and thought, oh, that's cool, and that kind of just inspired me to research this more. So our original goal was essentially just to prove this, but then we were able to prove the Kresch conjecture as well. So that was lucky. And then just one last note, I guess, is a note on the PHIJ formula. So this result implies a sort of complex formula here, a complicated formula, but it's a formula for the PHIJ in this Leonard pair. So kind of without loss of generality, you can assume this ordering, and you can also, to avoid trivialities, assume that they HI and J satisfy the triangle inequality. And then in that case, you get the PHIJ is equal to this messy thing here, the trivial positive factor, times a square of a certain 4F3. So that's kind of interesting factorization of the PHIJ. And then, again, another messy coefficient, but not that bad. There's no sums. And that's it. Thank you.